Hello everyone, I just wanted to point out before this video starts that about the first 20 minutes of this video are going to be concerned with the gamma function. I want to explain what the gamma function is, do a semi-derivation, a pseudo-derivation of where its integral representation comes from, and also explain some of the underlying principles of mathematical analysis that led to the gamma function itself, what analytic continuation is, and all that stuff. And so if you're already familiar with the gamma function, and you're not concerned about any of that, and you just were concerned about the information about the distribution, then this video is going to be timestamped, but feel free to skip through this information on the gamma function and head straight towards the derivation or the probability density function, all the other factors, or all the other properties of the gamma distribution. Welcome back to the series on statistics. Today's an exciting video, for me at least, because we're going to be talking about the gamma distribution. This is the point where I think that statistics starts to get very, very cool. And with just a little bit of pure mathematics, we're going to be able to describe a whole family of distributions that can describe a cornucopia of things in the real world. And so this is pretty interesting to me, at least. But the gamma distribution, what it is just a generalization of the exponential distribution. So with the exponential distribution, which we derived in the last video, we wanted to know how the time to the first occurrence of some event would be distributed if we know, on average, how many events are going to occur over some time interval. So if we are given some rate parameter, for instance, if we know that we're, on average, going to expect 5 calls during some time period, and we want to know, well, how is the time to the first call going to be distributed? Then we can calculate that with the exponential distribution. We can compute those probabilities. But what if we're not interested in the time to the first call, but instead we're interested in the time to the second or the third or the fourth or the alphth call? Well, that's where the gamma distribution is going to come into play. And so this is going to be a family of distributions that takes in 2 parameters. Now, instead of just the rate parameter that we had with the exponential distribution, we're also going to have something called a shape parameter. That's just going to be this alpha value here. It's telling you which event we are concerned with. And so if our alpha value is 3, we are concerned with the time to the third occurrence of an event, the distribution of the time to the third call that you receive, for instance. And so you can imagine that the case where alpha is equal to 1, that's going to tell you how the time to the first occurrence of an event is distributed, when you know on average how many over some time interval is distributed. And that is just the definition of the exponential distribution. So that's the relationship here. But before we work on deriving these details, I wanted to talk a little bit about the name of this distribution. We've seen before how with the exponential distribution, the exponential function shows up in the probability density function. If you look at the binomial distribution, then what we find is that the binomial theorem is useful in deriving that probability mass function. We find that if we look at the geometric distribution, we use geometric series in order to derive that probability mass function. And so these names have connections to this distribution, to these distributions. But now we have something called a gamma distribution. I don't know about you, but when I hear gamma, I think of radiation, I think of physics, I think of all kinds of gamma particles and fancy stuff. Maybe Fallout, the Fallout series. I don't know. I think of all these cool things. And so why does this distribution get such a strange name? This name is going to come from the gamma function, which, if you haven't heard of, that's, spoiler alert, that's what I'm going to be talking about first, because I think it's important to understand what the gamma function is. It's going to show up in the probability density function, but if we don't know what that is, then we're not going to understand the probability density function. We're not going to understand the distribution. So I'm going to take a few minutes now and talk about the gamma function, and then we will actually derive all the details of this distribution. It's not as bad as you might think. And so without further ado, let's get started with our discussion on the gamma function. Alright, so the gamma function is going to be the result of analytically continuing the factorial function. Analytical continuation is a tool that it comes from mathematical analysis. This is essentially extending the domain of a function to take in more values than it otherwise could. If that doesn't make sense, let's just talk about it a little bit. So this factorial function we should be very familiar with. This comes up all the time in probability. For instance, if you want to know how many ways you can order 4 objects, then there's 4 possibilities here, and then you'd have 3 possibilities here, 2 possibilities here, and then you'd only have 1 possibility left. And so it'd be 4 times 3 times 2 times 1, and this is just 4 factorial. And so stuff like this, the factorial function shows up in statistics all the time. combinatorics all the time, probability all the time. And analytic continuation, okay, so that's what the factorial function is. We know that in factorial is just going to be n times n minus 1 times n minus 2 all the way down to 1. And the factorial function is going to satisfy the property that n factorial is going to be equal to n times n minus 1 factorial. And so this is sort of that defining property of the factorial function, and this allows us to define it somewhat recursively or through induction so that we get to our original definition, which is just take that number and then subtract 1 and then just multiply down, and when you get to 1, you'll have your answer. Now, this function here is only defined for integer value, no, more particularly natural number values. For instance, if you want to take the factorial of a negative number, then that doesn't really make sense, because if you have negative 1 factorial, then what would this be? Well, according to this definition, it would just be negative 1 times negative 2 times negative 3, and then this would never go to 1, and this would just diverge. And so the factorial of a negative value doesn't make sense. And what about the factorial of a fraction? What if we wanted to do 1/2 factorial? Here, you would do 1/2, I guess, and then I guess you would do negative 1/2, sort of naively, and then you would do negative 3/4, and then once again, this would just diverge. And so this function only makes sense if we're dealing with positive integers, or those natural numbers. Otherwise, the factorial function does not make sense. And so this function has it's a countably infinite range. I mean, you could plug in, there's countably infinite amounts of natural numbers we could plug in here. But this function is going to only exist in discrete jumps. It's only going to exist at those natural number values and 0. Unless you include 0 in the natural numbers, in which case it's just the natural numbers. But what if we didn't want it to be like that? What if we wanted to preserve some property about this function, and particularly this property right here? We want this to be true, but we want to extend the domain of this function to where it can take in more values, where it can take in fractions, to where we can calculate, what if we wanted to know what pi factorial would be? Well, pi factorial is undefined, but we could define some new function that preserves this property here and is extended analytically to take in new values. Maybe we want to take in all real numbers instead of just natural numbers. And so that's the idea of analytic continuation, is we want to extend this function here to be defined on more values than just those natural numbers. And so you might think that that's an absurdly complicated concept. At least I do. But at least in this case, it's not that bad. Lines That Connect, I think is his name. It's a YouTuber on here who goes through in a lot of detail, he goes over the product form of the gamma function. So this tells you exactly how old mathematicians were able to analytically extend the factorial function to take in all real numbers as input. I highly recommend watching his video on the topic. It's very interesting, and it gives a good overview of analytic continuation if you're interested. But in that video, he doesn't talk about the more common form of the gamma function, which is the integral form. And so that's what I'm going to talk about here, and I'm going to try to explain why it sort of makes sense. All right, so I'm going to start with this integral here, and we're going to see why in a moment. I suppose this isn't a full derivation because you might not know why we would want to start with this integral, but if you'll grant that much, then you can see the logic from this step forward. And so we're going to start with this integral, and let's see what happens. This is a very easy integral to evaluate. We're evaluating with respect to t, so this just becomes 1 over s e to the st. That's this antiderivative, evaluated at 0. And I guess I should be specific here. This is t is equal to 0, and t is equal to infinity. And when t is equal to infinity, this will blow up to infinity, so this integral will diverge. But if we add the condition here, that we're only dealing with s values that are less than 0, then what's going to happen is this will go to 0 when t goes to infinity, because this will be e to the power of negative infinity, which is just 1 over e to the infinity, so it's going to go to 0. And so this is going to become equal to 0 at t is equal to infinity, and then when t is equal to 0, this is going to go to 1, and so we have 1 over s there, and so this would be 0 minus 1 over s, and then this is just equal to 1 over s. And so if we add this condition here, then this is what we get. We get negative 1 over s. I need to rewrite that. This is negative 1 over s. And so now what I'm going to do is I'm going to cut out the middleman here. And now that we've seen where that comes from, I'm just going to make this statement here, that these two expressions are equal to one another as long as we have this condition here that the s value is going to be less than 0. Okay, so now that we have that, what we want to do here is we want to differentiate both sides of this equation. But if we differentiate both sides with respect to t, this just becomes a constant, and so that's not really interesting. What we want to do is we want to differentiate with respect to s. And there is some theorem, I'm not going to prove it, but if we're differentiating this expression with respect to a variable that is distinct from the variable that we're integrating to, then we can actually just pull this derivative inside of the integrand, and that's okay, as long as the function is well behaved. I think there's some condition there, but this is just an exponential function, and so this is like continuous differentiable. It meets all the factors that probably need to be met for that to be the case. And so I'm not going to prove that because it's probably very complicated and uses a lot of analysis, but if you'll grant that as well, which I hope you do, then I just want to see what happens when we take the first derivative here with respect to s. Here we're differentiating with respect to s. This just becomes t e to the st dt. And then here on this side, we're differentiating with respect to s. This is just negative s to the negative 1 power. And so this is just the power rule. This becomes 1 over s squared. Now let's take the second derivative. Put a colon here, I suppose. This is going to tell us that the integral from 0 to infinity is going to be, here we're just going to pull out another t, so we're differentiating with respect to s. It's just the chain rule, dt. And then this is going to equal, and then what's going to happen here, this is s to the negative second power, and so this is going to become negative 2 over s to the third. And then if we differentiate one more time, do third, we're going to get the integral from 0 to infinity. This is the last one I'm going to do because hopefully the pattern will become clear. dt. And then this is going to equal, let's see, we would get 6 over s to the fourth. And so in general, the pattern here should become clear. In this numerator, we're multiplying by the next integer value. And so this value here is also 3 factorial. And then when we differentiate again, we're going to multiply by negative 4. And so this is going to become negative 4 factorial. And so the pattern here is that we have 1 factorial here, and then when we take the second derivative, we have negative 2 factorial. And then 3 factorial, negative 4 factorial. 5 factorial, negative 6 factorial. And you could continue this out if you don't believe me, but that is the pattern here. And so in general, what we're trying to say is that the nth derivative of this expression, we're going to integrate from 0 to infinity, and then this is going to be t to the n, because of that power, the chain rule. We're going to have to pull out n different t factors here, e to the st dt. This is going to be equal to n factorial over s to the n, but we have to keep in mind that this is alternating here, and so in order to keep track of that alternating positive and negative value, I'm going to add one condition here, which is I'll just add a negative 1, and then I'm going to raise this. I think I want to raise this to the nth power as well. I think so, because when I take the first derivative, it becomes positive. Okay, so here, if we want the first derivative to be positive, then when n is equal to 1, we want this to be positive. So let's make this n plus 1. But also, when we take the first derivative in the denominator here, we have s squared here. We don't have s to the first power, and then this is increasing just by 1 each time. And so this exponent here also needs to be an n plus 1. And so this is the expression that we get when we take the nth derivative. And now what we can do is, because the only condition that we needed to have here for this statement to be true was that our s value needed to be less than 0. That was what allowed this integral to diverge. And so let's just let s be negative 1. Let's let s be equal to negative 1. And then what's going to happen? Well, if we let s be equal to negative 1, then here we're going to have the integral from 0 to infinity of t to the n, e to the negative t, dt. And then what are we going to get here? We'll have negative 1 to the n plus 1. Then s becomes negative 1, so it's negative 1 to the n plus 1. And so we'll get some cancellation here. And what we'll be left with is n factorial. And so this is our factorial function. This is what we're interested in. But this function here, or this value here, I guess this function here, in factorial, we already explained how this is only defined on the natural numbers. But by defining it in this way, through this integral instead, this integral is defined for all real numbers. We can plug in negative values, we can plug in fractional values, we can plug in irrational values for n here, and we will get an answer. And so I guess the only thing to test is, does this still hold if we take this integral and we define this as something, so I'm going to call this pi of n, and I'm going to set this equal to this integral here. Set this equal to this integral here. Then essentially what we want to know is, does this function here still fulfill the property that pi of n multiplied by does this still satisfy the property that n times pi of n minus 1 is equal to pi of n? And we want to test this. And if it does, then we'll have found a function that satisfies the core property, this core property of the factorial function, but it's now no longer defined just for the natural numbers, but it's now defined for all real numbers. And so let's test that really quick. All right, so I'm not going to bother trying to actually compute this integral by hand. I don't think you can, but I'm not going to try. But here I just plugged in a couple values here. So here we have this pi function that we've defined here to be this integral evaluated at 1.5, and we get this output here, 1.32, etc. And then I wanted to evaluate it at n minus 1, so that would be 1.5 minus 1, so I evaluated it at 1/2. And I get this value here, which might look familiar to you. Now, if you take this value, or this value right here, and you multiply it by 1.5, we should expect to get this value, because that's the property of the factorial function that we would like to preserve. And if you plug that in, if you take this value here, and you multiply it by this 1.5, then what happens is we get the exact same answer as when we plug into the function evaluated at 1.5. And so this does indeed, this is just one example, this isn't a formal proof, but this integral here does indeed fulfill this property, and that's why we call this the analytical continuation of the factorial function. And indeed, if you plug in some normal value here, like 4, which is definitely defined for the factorial function, then you'll get the expected output of 24. And you can actually plot this. I plotted a little bit of this graph. I don't know why it's cutting off here, to be honest. This integral should extend here and then have some interesting behavior in the negative quadrants here. But for some reason, when I plotted it into Desmos, it didn't. But this is what we get. And if you look at this graph, you can see 0 factorial is equal to 1. That's defined there. And then 1 factorial is also equal to 1. 2 factorial is equal to 2. 3 factorial, that's equal to 6. And so then 4 factorial is 24, so it blows up. But all the points that are for the factorial function are on this curve. And then it just continues the curve to fill in for all these real number values between these points, and even for some negative values. It's not defined at the negative integers, but it is defined for some negative values. And if you follow this continuation, then you'll see that even for these real number values, for instance at 1.5 and 0.5, this property is preserved. And so this right here, this function that we've defined as the pi function, this is equal to n factorial. It's just defined on a much larger domain than the factorial function. But for all the values that are natural numbers, this is equal to n factorial. So this is the analytical continuation of the factorial function. And then we have another function called the gamma function. And the gamma function, I always mess up gammas. The gamma function of n is just going to be pi of n minus 1. And so gamma of n is just n minus 1 factorial, but analytically continued, so that factorial is still analytically continued to be defined for all real numbers. And so you might be wondering, why is this gamma function shifted to be off the factorial by 1? And so for instance, if I plug in the gamma of 4, what I will get is 4 minus 1 factorial. I'll get 3 factorial, which is 6. So this is the gamma function. And if you wanted to define it in terms of the integral, then analogously, we already have the expression for our pi function, which is our analytically continued factorial function. We could just take that and evaluate it like this, from 0 to infinity, and then we just plug in n minus 1 here. So this becomes t to the n minus 1, e to the negative t dt. Once again, this is just coming from this integral up here. But this right here, this is actually called the gamma function. And so this is gamma of n is just n minus 1 factorial. And if you're curious at all, like me, about why this function is defined to be n minus 1 factorial instead of n factorial, then this is a little excerpt from a book on the Raymond's zeta function, I believe. It might have information on the Raymond's the Riemann hypothesis, but this is a book on his zeta function. And here I noticed in one of these footnotes, actually I saw this on the Stack Exchange when I was looking for information about this, they pointed out that in one of these footnotes that unfortunately Legendre subsequently introduced the notion gamma of s for pi of s minus 1. His reasons for considering n minus 1 factorial instead of n factorial are obscure. Perhaps he felt more natural to have the first pole occur at s equals 0 than s equals negative 1. But, whatever the reason, this notion prevailed in France and by the end of the 19th century in the rest of the world as well. Gauss's original notation was what we just derived right here. And so, at least according to this book, and I saw some other answers that said some other explanations for why you would be more concerned with n minus 1 factorial. Something about how it's not actually n minus 1 and the exponent, but it's a dt over t, and then this dt over t was something called a Haar measure. But this is getting into measure theory and real analysis and all this stuff that I have no idea about. So I can't really speak on that. But at least according to that one book, this seems to be just a case of semantics. But now I hope we have a solid understanding of what the gamma function is. Because when we see the gamma function in this probability density function, I don't want you to just mindlessly plug it into this integral or be confused as to what that is. Now we will understand that's the analytic continuation of the factorial function, but shifted to be off by 1. And so now we should have an understanding of the gamma function, and I think we're ready to derive the gamma distribution. All right, so returning to our original situation here, let's just go over all the details and make sure we're 100% okay with everything that's going on. Here, the information that we have is that we know the expected number of events that occur over this time interval is going to be equal to lambda. And here I'm making the additional assumption that the length of this entire time interval here is going to be equal to 1. The reason I'm making this assumption is because, as we explained in the derivation of the exponential distribution, this rate parameter here is expected just to be a directly proportional to the length of this time interval. And so we can always just linearly scale this rate parameter here by some factor that we need, by whatever factor we need in order to make the length of the time interval equal to 1. In other words, if we were expecting 10 events to occur in a time interval of length 2, that's exactly the same as expecting 5 events to occur in a time interval of length 1. So we can always just scale this lambda to make this time interval here equal to 1, and we can draw our conclusions based off of that. Now, the reason we can make that assumption, the reason that we're assuming that this lambda here is directly proportional to the length of the interval, is because one of the assumptions we need to make here, and I guess I could pull those assumptions up. These are all our assumptions here. Our second assumption tells us that we are expecting there to be an equal likelihood of an event occurring at any point throughout the time interval. And so that tells us that we could just scale this lambda, and it should be proportional to this time interval. The other assumptions here are just going to allow us to approximate this as a series of subintervals that are getting smaller and smaller and smaller, and then we use the binomial distribution in order to estimate this problem. But that's actually a much more difficult way to approach this problem. So essentially, I just want to explain that this assumption here that the time interval is equal to 1 and that this lambda here can just be directly scaled is based off of that second assumption. But now let's get into the actual derivation of the cumulative distribution function. And so if we have S is a gamma distributed random variable with a shape parameter of alpha and a rate parameter of lambda, this is the way that the time to the alpha event is distributed, then let's compute the probability that s is less than or equal to t. And here it's just strictly less than, but it's actually going to be the same probability either way. Because it's a continuous random variable, the probability of it being equal to t is 0. And so let's get started. Alright, so the first thing I'm going to do is I'm going to appeal to the law of complementary probability and say that the probability of s being less than or equal to t, this is just 1 minus the probability of s being greater than t. And the reason I want to do that is because this probability here is actually a lot easier to see and compute, work with mathematically than this one. And the reason being is that this is telling us, let's think about what this means. The probability of s being greater than t, based on the definition of what s is telling us the probability that the time to the alphth event is greater than t. And so if the time to the alphth event is greater than t, then that tells us that the alphth event has not yet occurred in this time interval here, from 0 to t. Now, it doesn't matter if the first event occurred, or the second event, or the third, or the 100th. As long as alpha was greater than 100, then all those events can occur, and that's fine. The time to the alphth event would still be greater than t, as long as the alphth event has not occurred. And so we can model this with the Poisson distribution. And so all we need to do is we need to scale this rate parameter to be proportional to this interval here, and then that's going to give us the estimation of the number of events that will occur in this interval. And so that's going to be lambda t. And you might be thinking, shouldn't it be lambda divided by t? In this case, no, because we are conditioning that the length of the total interval here is equal to 1, and this little t here is less than that, so this is going to be some fraction of this interval. And so if we just take the length of this interval and multiply it by lambda, it will give us some number that's smaller than lambda, but directly proportional to the length of this interval. So this lambda here is going to be the expected number of events that will occur in this time interval from 0 to t. And so now we can use this lambda t to compute the probability mass function of the Poisson distribution for different expected numbers of events. And we want to do that, we want to sum up over all the possibilities where the alphth event has not yet occurred. And so if we were going to do that, we would do 1 minus, and then here we would sum up over the possibility, the probability that no event occurs, that one event occurs, that two event occurs, all the way up to alpha minus 1. Because if alpha minus 1 event occurs, that's fine. But if alpha events occur, then the time to the alphth event is less than or equal to t. It would be contained in this interval if we were to sum up there. And so we want to sum up over all these possibilities where the alphth event had not yet occurred, because that's going to suggest that the time to the alphth event is greater than s. And so here, this is just the definition of the Poisson distribution. That's going to compute the probability of 0 events occurring in this interval based off of this rate parameter, 1 event occurring all the way up to alpha minus 1. And the probability mass function for a Poisson distribution is just our rate parameter, which in this case is lambda t to the kth power, times e to the negative lambda t. And then we're going to divide by k factorial here. And so this expression here is going to be it's a precise estimation for, or a precise answer for our cumulative distribution function. But once again, similar to our exponential distribution derivation, we're going to work with this to get it in terms of a continuous function that's much more conventional. And so our cumulative distribution function, our capital F t here, is going to be equal to the probability of big S being less than or equal to t, which is equal to 1 minus, and then the first thing I'm going to do is I'm just going to pull out this k is equal to 0 here. When k is equal to 0, this term will go to 1, this will go to 1, and so we'll just be left with e to the negative lambda t. And so we're going to have an e to the negative lambda t here, and then we're going to have a sum that now is just going to go from 1 to alpha minus 1. And then the rest will be the same. And we know that the cumulative distribution function here, if we were to differentiate this with respect to t, then we'll just get our probability density function. And so in other words, our PDF for a gamma distribution is just going to be equal to the derivative here with respect to t. And if we differentiate this with respect to t, this is just a constant. And then we pull out the negative lambda, and we get lambda e to the negative lambda t, which should look familiar. and then this should be a negative here because we pulled out the first value, but the rest is still a negative sum. And so this is going to be minus the sum. And I'm just going to pull this derivative with respect to t inside the sum, and I'm going to pull out the factors that do not depend on t. So this is going the sum from k is equal to 1 to alpha minus 1, and I'll pull out this 1 over k factorial, and then we're differentiating here with respect to t. What are we differentiating? We have lambda t to the kth power times e to the negative lambda t. And then this looks very complicated, but this is just the product rule. And so this here, the rest of this is going to stay the same. And so I'll add this back in. I'm just going to copy most of this. And so this derivative here is just the product rule. And so the derivative of this term here would be k, this would be k times lambda t to the k minus 1th power. But then by the chain rule, we have to pull this lambda out since we're differentiating with respect to t. So you get lambda k times lambda t to the k minus 1th power multiplied by this function, multiplied by e to the negative lambda t. And then we're going to add here the derivative of this function, which is going to be negative lambda e to the negative lambda t. So I'm just going to subtract lambda e to the negative lambda t, and then I'll multiply by this function here, multiply by lambda t to the kth power. And then one thing I'm recognizing here is that this negative is being applied to this entire summation, so I can just bring this negative into the summation, and I can essentially just swap these terms. And so I'll find that this probability density function is equal to e to the lambda e to the negative lambda t plus the sum from k is equal to 1 to alpha minus 1 of 1 over k factorial. And then in here, instead of this, I'm just going to swap these. So this will become positive and this will become negative as I distribute this negative. And so this is going to be, we'd have lambda t to the kth power, lambda t to the kth power multiplied by lambda e to the negative lambda t. And then now I'm subtracting lambda k, lambda t to the k minus 1th power multiplied by e to the negative lambda t. Okay, this is extremely messy. And this is not the form that we want our probability density function to be expressed in. Ideally, we would like a nice continuous clean function that we could just plug into some sort of graphing calculator, something that we could plug into in a computer program to solve for these definite integrals and get us a probability. And this sum is going to make things very wonky. And it's not immediately obvious how to proceed from here. And one of the things we can sort of do, if you were to stare at this sum and really scratch your head for a while, one of the things you might think to do is, well, what if we expand out this sum? Maybe there'd be some pattern that we might recognize. And so I'm going to trust that everybody watching this video, if you're taking mathematical statistics or you're interested in this level of mathematics, then I'm trusting that you're capable of plugging in a 1, plugging in a 2 for these values of k's here. And so I'm just going to do that right now, but I'm not going to bore the audience with me just going through the arithmetic of seeing what happens when I plug in k equals 1, k equals 2. So I'm going to do that for the first couple terms and show you guys what the pattern is that results from that. All right, so essentially what happens here is you can factor out this e to the negative lambda t, so that doesn't depend on k. And then what we're left with is this pattern here of lambda to the k plus 1, is t to the k, over k factorial, minus lambda to the k, t to the k minus 1 over k minus 1 factorial. And what's going to happen here is this kth term, this term here is going to be positive. And then in the k plus 1th term, if I were to plug in k plus 1 for k here, then this would be lambda to the k plus 1, t to the k, so that's the numerator here, and then this would be k factorial in the denominator, and this term is negative. And so the k plus 1th term, the negative portion of the k plus 1th term is going to cancel with the positive portion of the kth term, and we'll get this cancellation factor going on throughout the sum. And so just to sort of illustrate that, I've expanded out the sum. And so here we have this positive lambda squared t that's going to cancel with this negative. And so this is going to cancel. And then this is a lambda cubed t squared over 2. That's going to cancel with this negative lambda cubed t squared over 2. And so all of these are going to all cancel. And the only one we're going to be left with is the positive term of the last term in this sequence, as well as, I guess, this negative lambda here. But what's going to happen is that negative lambda is going to multiply by this and cancel with this term here. And so, but essentially all we'll be left with is this negative lambda, and then the positive term of the alpha minus 1th term in this sum. And so let's make that summation here. We'll get lambda e to the negative lambda t plus e to the negative lambda t. And then everything's going to cancel except for this negative lambda and the positive term from the alpha minus 1th term in, or the positive part of the alpha minus 1th term in this sum. And so alpha minus 1, we're going for k here. We have alpha minus 1 plus 1. That's just lambda to the alpha. And then we have t to the alpha minus 1. T to the alpha minus 1. And then we're dividing by alpha minus 1 factorial. And then when I multiply this out, what's going to happen is that here we'll get lambda e to the negative lambda t minus lambda e to the negative lambda t. And so this is going to cancel with this. And we'll just be left with, let's see, I'm going to pull out all the constants. Lambda to the alpha, these are both just constants, divided by, and I guess e to the negative, no, that's part of the function. So lambda to the alpha divided by alpha minus 1 factorial. And then this is going to be multiplied by t to the alpha minus 1 e to the negative lambda t. And so this here is our functional representation of the probability density function. This is our probability density function for the gamma distribution. I know it was a really long walk to get here, but I spent a lot of that time just really trying to lay the conceptual groundwork here. The mathematical derivation here, it didn't feel like it took that long. The hardest part was just contending with this sum. But this is the probability density function for a gamma distribution with a shape parameter of alpha and a rate parameter of lambda. All right, I did want to make some final notes before we move on here. The rest of this video is going to be a lot faster. I'll go through the moment generating function, the mean, and the variance pretty quickly because they're actually a lot easier than you might expect for this distribution. But this is probably the most important equation here, is the probability density function. And so I did want to point out that here, there's a couple different ways you might see this. This is a perfectly valid way of representing this. But in addition to this, we could say that, as we established in the beginning of the video, alpha minus 1 factorial, that's just gamma of alpha. That's the definition of the gamma function. And so we can use the gamma function here in our definition. And that's kind of where we get this gamma distribution. That's where the name comes from, is because the gamma function shows up here. So this is just lambda to the alpha over gamma of alpha, t to the alpha minus 1, e to the negative lambda t. And so this is the probability density function for gamma distribution with the gamma function instead of the alpha minus 1 factorial, noting that these two are equivalent. The other thing we probably want to point out here is that here we're using the rate parameter, and the rate parameter is the number of expected events that occur in some time interval. But it might be more useful in some experiments to work with, instead of the rate parameter, the amount of time you would have to expect to wait before your first occurrence of an event. And the amount of time you would expect to wait before the first occurrence of an event, that's just the expected value of the exponential distribution, which tells you the amount of time, or how the amount of time to the first occurrence of an event is distributed. So the expected value of an exponential distribution will give you the amount of time that you have to wait for the first occurrence of an event, or the expected amount of time you have to wait until an event occurs. And we know that the expected value of an exponential distribution is just 1 over lambda here. So it might be useful to define a new parameter here. Typically this one is called theta. And theta is just the mean of an exponential distribution, which is 1 over lambda. This is the expected amount of time you'd have to wait. And if we make this substitution here, then lambda here becomes 1 over theta. And we could plug this in for lambda here to get a probability density function for the gamma distribution in terms of the expected amount of time before an event occurs. And so if we make that substitution here, we have that the probability density function for t, this is just going to be equal to, instead of lambda here, we'd have 1 over theta to the alpha power. And so this would become t to the alpha minus 1, e to the negative t over theta. And then we'd be dividing by, and then here we have theta to the alpha times gamma of alpha. And so this is an alternative way of representing this. not in terms of the rate parameter, but in terms of the expected time to the first occurrence of events. So these are the most popular ways you'll see the probability density function represented for the gamma distribution. And so now let's move forward to deriving a couple properties here. And like I said, that's going to go a lot faster than the derivation for the probability density function. All right, so essentially all these properties that we're interested in, the mean, the variance, the moment generating function of gamma distributions, they're going to follow almost immediately just from the definition of the gamma function, which we went over in the beginning of this video. And so gamma of alpha, just as a reminder, is just equal to this integral here. And that should evaluate to alpha minus 1 factorial if alpha is indeed a natural number, not including 0, I guess. So I guess I should do minus the set including 0. But that's just a technicality. In general, if alpha is a natural number, then this integral will evaluate to alpha minus 1 factorial. But this integral here is going to allow us to compute some of these properties. And so let's see what that looks like with an example. Let's let S be a gamma distributed random variable with a a shape parameter of alpha and a rate parameter of beta. Here I'm using beta instead of lambda. I used lambda in the beginning of this video because I wanted to emphasize the connection with the exponential distribution. It is exactly the same variable that we're trying to characterize about the real world. It's the rate parameter, but typically you'll see beta when you're dealing with gamma distributions. That's the way that most people denote the rate parameter with respect to gamma distributions. I'm not sure why they use a different variable with gamma distributions conventionally than they do with exponential distributions when they're in fact the same thing. But you're going to see it both ways, so I wanted to show it both ways in this video. So here I'm just letting S be gamma distributed with shape parameter alpha, rate parameter beta, and let's compute our moment generating function. The moment generating function of S here is just going to be equal to, by the law of the unconscious statistician, we'll integrate over all the values in the support, and then by the law of unconscious statistician, this is just the expected value of E to the S times our random variable, and so this is just E to the S with a dummy variable here, and then we're multiplying by the probability density function of the gamma distribution. And so let's see if I can get this from memory. I think we're going to have our rate parameter to the power of our shape parameter divided by gamma of the shape parameter. And then here we'll have t to the alpha minus 1, e to the negative beta t, I think. Hopefully I got that right, otherwise I'm going to have to redo this section of the video. But going from memory, that looks correct to me. Okay, the first thing to notice here is that this beta and this alpha, these are just constants. In gamma of alpha, that's just alpha minus 1 factorial, alpha is a constant, and so this whole term is just a constant. And so we can pull this whole thing out. And so this winds up being equal to beta of alpha, beta to the alphath power over gamma of alpha. And then inside this integral here, now that we've pulled out that constant, we can multiply this e and this e together. And so we'll get t to the alpha minus 1. It's horrible. T to the alpha minus 1. And we get e. And then what would we have? We'd have st minus beta t. So that's just t times s minus beta dt. And now this is the fact that I want to point out. This is the definition of the gamma function. And look how similar it is to this right here. And so essentially, if we could just get this to look a little bit more like this right here, then we'll be in business. And we could just, instead of even having to evaluate this integral, we could just use the definition of the gamma function, and then we'll be done with this whole section and we can finish our derivation for the moment generating function. And so how can we get this to look like this? Well, the first thing I want to do is I want a negative t instead. And so I'm going to swap these, pull out a negative 1, and so it'll become beta minus s here, beta minus s, and then I'll pull a negative right there. And then I'm going to make a u substitution, where u is going to be equal to beta minus s times t. And then what would du become? Du here would be equal to beta minus s dt. And by just algebra here, we'd have dt is equal to du over beta minus s. And then what would we have? The other thing here is that we'd have a t here. and t has some relationship to u. So t would become u over beta minus s. Okay, and then the last thing we need to check are just the bounds of this integral. So as t tends towards infinity, what happens to u? As t tends towards infinity, we're just being multiplied by some constant. So as long as beta is greater than s, then this du here, or this u will also go to infinity. And if t tends towards 0, then u is also going to tend towards 0. And so we've checked the bounds of the integral, everything seems appropriate, and now we can just make this substitution. And so this is going to be equal to beta to the alpha power over gamma alpha. And then the bounds of the integral do not change, going from 0 to infinity. And now we plug in our value for t. We get u to the power of alpha minus 1 over b to the s to the power of alpha minus 1. And so this is going to be u to the alpha minus 1 over beta minus s to the alpha minus 1. And then we're multiplying by e to the, now this is just negative u. And then here, our du here, or dt is going to be equal to du, but we also have this 1 over b minus s here. And they have a b minus s here, and so 1 over b minus s times 1 over b minus s to the a alpha minus 1th power is just going to be b minus s to the alpha power. And so that's going to be that right there. And then now we can factor out this beta minus s to the alpha power, because once again, that is just a constant. And so this becomes beta to the alpha over gamma alpha times beta minus s to the alpha power. And then what will be left with in this integral, we're integrating from 0 to infinity of u to the alpha minus 1 e to the negative u du. And then this right here, this is just a definition of gamma of alpha. I kind of messed that up in the beginning, but this should be an alpha minus 1. I was thinking of our pi function earlier. This is the definition of the gamma function. And so this is our definition of the gamma function right here. And so this is just gamma of alpha. And so what happens is the whole integral just goes away. It's equal to gamma of alpha. And then that gamma of alpha is going to cancel with this gamma of alpha. And we'll be left with the moment generating function, beta to the alpha over beta minus s to the alpha power. Alternatively, you could just do beta over beta minus s and raise that whole expression to the alpha power. And alternatively, because this is beta over beta minus s to the alpha power, we can flip this and then take that to the negative alpha power, because that's the same as taking the... So essentially, if we were to flip this, we'd have beta minus s over beta, and then this would be raised to the negative alpha power, because this is the same as taking the reciprocal of this to the alpha power. And that's exactly... So these two expressions are exactly the same. And then this reduces to a form that's very, very common, which is 1 minus s over beta to the negative alpha power. And so this is our moment generating function, probably in the most common form here, but I've also seen this form as well. This is the moment generating function for a gamma distribution. And so the only trick here was to use the definition of the gamma function, which I apologize for messing up in the beginning, but this should have been a minus 1. But if we just appeal to the definition of the gamma function, then we can compute these very easily. And you can do this as well. If we weren't solving for the moment generating function, but we were instead solving for the mean, then we would just plug in a t here, and this would be t to the alpha. And then we just do the exact same steps. You factor out the constant, and you make this look like the gamma function. And then you solve it. But I'm not going to do that. I'm just going to use the moment generating function in order to derive the first and second moments. And so the mean is just going to be the first moment. And so we would just differentiate this moment generating function with respect to s. And this is going to be very easy. Just 1 minus s over beta to the negative alpha power. And so this is just the chain rule. We have negative alpha times 1 minus s over beta to the negative alpha minus 1th power. And then when we're doing this derivative here, we have the chain rule as well. So we have to multiply by the coefficient on the s inside the term here, which is negative 1 over beta. And so these negatives will cancel, and we'll get alpha over beta. And we'll get alpha over beta. And while my brain is working in derivative modes, I'm just going to take the derivative again. So I'll do, I guess, an arrow, and I'll do d2 ds. And the second derivative here, we'll just take this derivative once more. I'm going to pull down this factor. This becomes negative alpha plus 1. That's the same as negative alpha minus 1 times alpha over beta, multiplied by 1 minus s over beta to the negative alpha minus 2, the negative alpha minus 2 power. But then we need to multiply by the derivative of the inside, which once again is negative 1 over beta. And so the negatives will go away. Negatives will go away, and then we'll have a beta squared in the denominator. And so the second derivative here is just going to be alpha plus 1 times alpha over beta squared. And so now if we want the mean and the variance, then the mean is just going to be the first moment evaluated at s is equal to 0. When s is equal to 0, this becomes 1 to some power, and 1 to every power is just 1. So the mean here is going to be equal to alpha over beta. For the shape parameter divided by the rate parameter, we get some nice properties there. And then the variance here is going to be equal to the second moment, which is the second derivative of the moment generating function evaluated at s equals 0. And so once again, when s is equal to 0, this goes to 1 to some power. That's just 1. So this whole thing goes to 1. And then we'll be left with alpha plus 1 times alpha. Otherwise, alpha squared plus alpha over beta squared. And then we need to subtract by the first moment squared. And so what happens is the alpha squared cancels with the alpha squared, and we get the variance is equal to alpha over beta squared. And so this is the variance of a gamma distribution. This is the mean. And then this right here is our moment generating function. And so, like I said, this is pretty quick once we get the moment generating function. But it wouldn't be that bad to go through and do this process in order to calculate the mean and the variance as well, for the mean in the second moment, and then from there you can get the variance. But I think it's nicer just to go with the moment generating function. It's a pretty quick calculation for the gamma distribution. All right, so I hope you guys enjoyed this video on the gamma distribution. I know I spent a lot of time trying to, like I said, lay that conceptual groundwork and really understand where this probability density function is coming from, really understand this gamma function. But I think that's important for fully understanding all the properties of this distribution. Thank you guys for watching, and I'll see you all in the next one.